Look up at the stars tonight, and you'll see a glittering tapestry of light, galaxies swirling, stars burning, cosmic wonders stretching as far as the eye can see. But here's the astonishing truth. What you're witnessing is barely the surface of reality. The universe is hiding a secret, one so profound it rewrites everything we thought we knew about the cosmos. Nearly 85% of all matter in existence is completely invisible to us, a ghostly presence known as dark matter. It doesn't emit light, reflect it, or interact with the electromagnetic forces we rely on to observe the universe. Yet without it, galaxies would fly apart, stars would scatter, and the very fabric of space would unravel. This is the phantom galaxy paradox, the unsettling realization that the universe we see is just a shadow of what's truly out there, shaped by forces we can't even detect. How do we know dark matter exists if we can't see it? The answer lies in the way galaxies move, the way light bends around empty space, and the way the cosmos behaves in ways that defy the laws of physics as we understand them. Take our own Milky Way. It spins so fast that, by all rights, it should tear itself to pieces, but something invisible is holding it together, an unseen scaffold of dark matter, weaving through the galaxy like an invisible hand keeping the stars in place. And it's not just our home galaxy. Across the universe, galaxies cluster in patterns that shouldn't be possible unless vast, hidden structures are pulling them together. These are the fingerprints of dark matter, the silent architect of the cosmos. For decades, scientists have been racing to uncover the truth behind this enigmatic substance. Is it a particle we've yet to discover? A flaw in our understanding of gravity? Or something even stranger beyond the reach of current physics? The quest to solve this mystery has led to some of the most ambitious experiments in history: underground detectors waiting for a single, elusive interaction, telescopes mapping the invisible web of dark matter stretching across the universe, and simulations recreating the birth of galaxies under its influence. This isn't just a story about science. It's a detective story on a cosmic scale, one that challenges us to rethink the very nature of reality. So, let's dive into the shadows and explore the unseen forces that shape everything we know and everything we don't. Think of dark matter as the silent scaffolding of the universe, an invisible framework holding everything together, while ordinary matter, the stuff of stars, planets, and even our own bodies, makes up less than 5% of the cosmos. Dark matter outweighs it by more than 5 times. Yet, despite its overwhelming presence, it slips through our detectors like a ghost. It doesn't collide with atoms, absorb starlight, or leave any trace in the electromagnetic spectrum. So how do we even know it's there? The answer lies in gravity's relentless pull. Take a spinning galaxy, for example. The stars on its outer edges move at speeds that defy logic. According to the laws of physics, these stars should be flung into the void unless something unseen is anchoring them in place. That something is dark matter, an immense halo of invisible mass enveloping galaxies like an unseen glove. Astronomers first glimpsed this phenomenon decades ago when they noticed galaxies rotating too fast for their visible matter alone. The math simply didn't add up unless there was far more mass hiding in the shadows. But dark matter's influence doesn't stop there. When we look at galaxy clusters, colossal gatherings of hundreds or even thousands of galaxies, we see them bending light around them in ways that visible matter alone could never explain. This effect, called gravitational lensing, acts like a cosmic magnifying glass, warping the light from distant objects behind the clusters. The amount of bending reveals just how much unseen mass is at work. And time after time, the numbers point to dark matter as the missing piece. So what could this elusive substance actually be? Some theories suggest it's made of particles we've yet to discover, perhaps WIMP, or weakly interacting massive particles that barely interact with normal matter except through gravity. Others propose axions, ultra-light particles drifting through space like an invisible mist. There's even the radical idea that dark matter isn't a particle at all, but a sign that our understanding of gravity itself is incomplete. One thing is certain, solving this mystery could rewrite the textbooks. Dark matter isn't just a cosmic curiosity, it's the hidden architect of the universe, shaping galaxies, guiding their movements, and determining the fate of everything we see. Without it, the night sky as we know it wouldn't exist. And as scientists continue to hunt for clues, from deep underground labs to the farthest reaches of space, one question lingers: what other secrets is the universe keeping from us? The phantom galaxy paradox forces us to confront one of astronomy's most baffling riddles. Why do galaxies move as though they're weighed down by invisible anchors? Picture a merry-go-round spinning so fast that the riders should be flung off, yet somehow they cling on without explanation. That's precisely what happens in galaxies. Stars on the outer edges whip around their galactic centers at velocities that should send them hurtling into the void. According to Newton's laws, the visible matter in a galaxy, its stars, gas, and dust, simply doesn't provide enough gravitational glue to hold these speeding stars in place. The math screams that something's missing. This discrepancy first caught scientists' attention in the 1930s, when astronomer Fritz Zwicky noticed something peculiar about the Coma cluster, a massive gathering of galaxies. The individual galaxies within it were moving so rapidly that the cluster should have torn itself apart long ago. Zwicky coined the term dark matter to describe the unseen mass he believed must be holding everything together. Decades later, Vera Rubin's groundbreaking work on galaxy rotation curves confirmed the anomaly wasn't a fluke, it was universal. Every spiral galaxy she studied exhibited the same impossible speeds, as if an invisible hand were steadying the cosmic carousel. But the paradox goes deeper than just fast-moving stars. When light from distant galaxies passes near massive galaxy clusters, it bends dramatically, like a straw in a glass of water. This gravitational lensing effect reveals hidden mass distorting the fabric of space-time far more than the visible matter accounts for. It's as if we're seeing the shadow of a giant but can't spot the object casting it. Even the large-scale structure of the universe, the vast cosmic web of filaments and voids, couldn't have formed without dark matter's gravitational scaffolding. Ordinary matter alone would have taken far longer to clump together under gravity's weak pull. So where does this leave our understanding of physics? Some researchers argue dark matter must be a new type of particle, one that interacts only feebly with ordinary matter except through gravity. Others propose more radical solutions, like modifying Newton's laws of motion on galactic scales, a theory known as modified Newtonian dynamics, or MND. Yet MND struggles to explain all the observations, leaving dark matter as the leading explanation. The paradox persists because, while we've mapped its gravitational fingerprints everywhere, dark matter itself remains tantalizingly out of reach. It's the universe's greatest game of hide and seek, and we're still learning the rules. What makes the phantom galaxy paradox so thrilling is its sheer audacity. It's not just a gap in our knowledge, it's a chasm, forcing us to question the very laws we thought governed reality. Every time we think we've pinned down the cosmos, it whispers back, there's more to the story. And that's what drives scientists to peer deeper into the darkness, searching for the invisible threads weaving the universe together. The story of dark matter begins not in the vast emptiness of space, but in a small California observatory nearly a century ago. Fritz Zwicky, a sharp-witted astronomer with a reputation for thinking outside the box, was studying the Coma Cluster, a dense gathering of thousands of galaxies, when he stumbled upon something bizarre. The galaxies were moving far too quickly, zipping around the cluster's center at speeds that defied all expectations. According to the visible mass of stars and gas, the cluster's gravity should have been far too weak to hold them together. Zwicky did the math, and the numbers didn't just suggest a discrepancy, they screamed it. The cluster needed at least 10 times more mass than what telescopes could detect to explain the galaxy's frenetic motion. He called this missing mass Dunkelmaterie, German for dark matter, a term that would echo through astronomy for decades to come. But Zwicky's bold claim was met with skepticism. Without concrete proof, many dismissed his idea as speculative. It wasn't until the 1970s that the puzzle resurfaced, this time in the hands of Vera Rubin, a determined astronomer who faced her own share of resistance in a male-dominated field. Rubin's meticulous observations of spiral galaxies revealed an even more perplexing pattern. Stars at the edges of galaxies were orbiting just as fast as those near the center, a phenomenon that Newton's laws couldn't explain. If galaxies were made only of the matter we could see, those outer stars should have been drifting away, slowed by the weakening grip of gravity. Instead, they raced along as if pulled by something unseen. Rubin's findings were undeniable. Galaxies were wrapped in massive halos of invisible matter, a ghostly presence shaping their very motion. These discoveries didn't just challenge existing theories, they shattered them. Zwicky and Rubin had uncovered a cosmic conspiracy, a hidden architecture woven into the fabric of the universe. Their work forced scientists to confront an unsettling truth: the cosmos as we knew it was incomplete. The visible stars, the glowing nebulae, even the planets under our feet, they were merely the tip of the iceberg. Beneath it all lay a vast, invisible realm holding everything together. Today, their legacy lives on in the cutting-edge experiments hunting for dark matter's elusive nature. From underground labs shielded from cosmic interference to space telescopes mapping distortions in ancient light, the search has become one of science's greatest quests. And while we still haven't found the smoking gun, every failed detection, every unexpected twist in the data, brings us closer to unraveling the mystery. After all, that's how science works, not through sudden revelations, but through the slow, persistent chipping away at the unknown. And who knows, the next breakthrough might be just around the corner, waiting for another curious mind to shine a light into the darkness. Imagine a sculptor shaping clay, but instead of hands, the artist uses an invisible force to mold every curve and contour. That's the role dark matter plays in the universe, an unseen sculptor guiding the birth and evolution of galaxies. While stars and gas clouds are the glittering end result, it's dark matter that lays the foundation, creating gravitational wells where ordinary matter can gather and ignite into the galaxies we see today. Without this hidden framework, the cosmos would look utterly different, a scattered, formless void instead of the structured tapestry we call home. Take the Milky Way as an example. Our galaxy isn't just a random swirl of stars. It's a carefully balanced structure with spiral arms tracing elegant arcs around a dense central core. But what keeps those arms from unraveling? The answer lies in the colossal halo of dark matter surrounding our galaxy, a vast and invisible presence whose gravity acts like an anchor, stabilizing the entire system. Computer simulations show that when dark matter is removed from these models, galaxies like ours simply can't hold their shape. Stars fling outward, spiral arms disintegrate, and the elegant order we observe collapses into chaos. This invisible scaffolding doesn't just hold galaxies together, it also determines how they cluster and interact. Across the universe, galaxies aren't scattered randomly. They're strung along immense filaments of dark matter, like beads on a cosmic necklace. These filaments form a sprawling web, with galaxies congregating at the intersections where dark matter's gravitational pull is strongest. It's a pattern so consistent that astronomers can predict where new galaxies will be found simply by mapping the unseen gravitational landscape. But dark matter's influence goes even deeper. When the universe was young, tiny fluctuations in the density of dark matter created the seeds for all future structure. Ordinary matter, buffeted by radiation and heat, couldn't clump together effectively on its own. But dark matter, unaffected by light or heat, began gathering into faint ripples that would eventually grow into the gravitational wells where galaxies were born. Over billions of years, gas and dust cascaded into these wells, igniting into stars and forming the galaxies we recognize today. What's truly astonishing is how precise this process had to be. The amount of dark matter in the universe, its distribution, and even the way it interacts with gravity had to fall within an incredibly narrow range for galaxies like ours to exist. Too much dark matter and galaxies would collapse into dense knots too soon, too little, and they'd never form at all. It's as if the universe followed a hidden recipe, one we're only beginning to decipher. Yet for all its power, dark matter remains frustratingly elusive. We see its effects everywhere, from the rotation of galaxies to the bending of light around galaxy clusters. But what it's made of, how it behaves beyond gravity, these questions linger at the frontier of science. Some theories suggest dark matter particles could collide and annihilate, releasing faint bursts of energy we might detect. Others propose it could interact with itself through unknown forces, creating intricate substructures within its halos. One thing is certain: dark matter isn't just a passive backdrop to the universe. It's an active architect shaping the destiny of galaxies with every passing moment. And as we peer deeper into the cosmos, we're not just mapping stars and gas, we're tracing the outlines of something far grander, an invisible hand guiding the dance of the universe itself. If dark matter is truly a particle, what would it look like? Scientists have spent decades theorizing and hunting for possible candidates, each with its own unique properties and challenges. One of the leading contenders is a class of particles known as WIMP, weakly interacting massive particles. These hypothetical particles are thought to be heavy, slow-moving, and incredibly shy, barely interacting with normal matter except through gravity. Their name says it all. They're massive enough to exert a gravitational pull, yet so weakly interacting that they slip through ordinary matter like ghosts through walls. The hunt for WIMP has driven some of the most ambitious experiments in physics. Deep underground, shielded from cosmic rays and other interference, detectors filled with ultra-pure liquids or crystals wait patiently for the rare moment a WIMP might collide with an atomic nucleus. These collisions would be incredibly faint, just a tiny shudder in the detector, but if caught, they could finally reveal dark matter's identity. Yet, despite decades of searching, WIMP remain elusive. Every null result narrows the possibilities, forcing scientists to rethink their assumptions. Maybe dark matter isn't as massive as we thought. Maybe it interacts even less than predicted. Or maybe, just maybe, we're looking for the wrong thing entirely. That's where axions come in. Unlike WIMP, axions are theorized to be incredibly light, billions of times lighter than an electron floating through space like an invisible mist. They were originally proposed to solve a completely unrelated puzzle in particle physics, but their properties make them a compelling dark matter candidate. Axions wouldn't bump into atoms like WIMP might. Instead, they could transform into photons, particles of light, in the presence of strong magnetic fields. Experiments like the Action Dark Matter experiment, or ADMX, use powerful magnets and ultra-sensitive detectors to listen for this faint whisper of conversion. It's like tuning a radio to a frequency no one has ever heard, hoping to catch a signal from the unseen universe. Then there's the Large Hadron Collider, the world's most powerful particle smasher. While its primary mission is to explore the fundamental building blocks of the universe, it also has the potential to create dark matter particles in high-energy collisions. The catch: dark matter wouldn't leave a direct trace in the detector. Instead, scientists look for imbalances, moments when energy and momentum seem to vanish, as if carried away by something invisible. It's a bit like hearing rustling leaves but seeing no wind, hinting at a presence just beyond perception. The diversity of these approaches reflects the enormity of the challenge. Dark matter could be one particle, many, or something entirely unexpected. Some theories even suggest it might not be a particle at all, but a shadowy mirror universe with its own set of physical laws, barely overlapping with ours. Each dead end in the search forces us to expand our imagination, to consider possibilities that once seemed outlandish. What makes this quest so thrilling is its unpredictability. Every experiment, whether it succeeds or fails, reshapes our understanding of the cosmos. And while we haven't found definitive proof yet, the search itself has already transformed physics, pushing the boundaries of technology and theory alike. After all, the universe rarely gives up its secrets easily, but that's what makes the hunt so extraordinary. Gravitational lensing is like the universe's way of drawing with invisible ink, revealing hidden structures through the warping of light itself. Imagine holding a magnifying glass over a page of text, watching the letters stretch and bend as light passes through the curved glass. Now, picture that on a cosmic scale, where entire galaxies act as the lens, distorting the light from objects billions of light years behind them. But here's the catch: the amount of bending we observe often far exceeds what the visible matter in those galaxies could possibly produce. That discrepancy is the smoking gun for dark matter's existence. When astronomers first noticed this phenomenon, it was as if the cosmos had handed them a treasure map. By meticulously measuring how light from distant quasars or galaxies twists around foreground clusters, they could trace the gravitational pull of unseen mass. The most striking examples are Einstein rings' perfect, halo-like distortions where light from a background object gets bent into a complete circle around a massive foreground galaxy. These rings aren't just beautiful, they're precise cosmic scales, revealing exactly how much dark matter is packed into the lensing galaxy. And time after time, the numbers confirm that what we see is only a fraction of what's truly there. But gravitational lensing does more than just prove dark matter's existence. It lets us map its invisible architecture. Take the bullet cluster, one of the most dramatic pieces of evidence. This cosmic collision, where two galaxy clusters slammed into each other, left a trail of clues visible in X-rays and lensing data. The hot gas from the clusters, detectable through its X-ray emissions, lagged behind during the collision, slowed by friction. But the dark matter, unaffected by electromagnetic forces, sailed right through, leaving its gravitational imprint on the bent light of background galaxies. The result, a clear separation between ordinary matter and the unseen mass, like a fingerprint left in the fabric of space-time. This technique has become so refined that astronomers now use it to create detailed dark matter maps across the universe. By combining observations from telescopes like Hubble and the James Webb Space Telescope, they've uncovered vast, web-like structures of dark matter stretching across billions of light years, a cosmic skeleton holding everything together. Even more astonishing, some of these maps reveal dark matter where no galaxies are visible at all, hinting at hidden pockets of the universe waiting to be discovered. What makes gravitational lensing so powerful is its universality. Unlike particle detectors or colliders, which rely on specific interactions, lensing works purely through gravity, the one force dark matter can't hide from. It's a reminder that even in the darkest corners of the cosmos, light finds a way to expose the truth, and as our telescopes grow more sensitive, who knows what other secrets they'll unveil. The universe's invisible scaffolding is finally coming into focus, one bent photon at a time. What if dark matter isn't the answer at all? What if, instead of an invisible substance shaping the cosmos, our understanding of gravity itself is incomplete? This radical idea lies at the heart of modified Newtonian dynamics, or WIMPs, a theory that dares to rewrite one of physics' most fundamental rules. Proposed in the 1980s by physicist Mordechai Milgram, WIMPs suggests that gravity doesn't weaken as quickly over large distances as Newton's laws predict. On the scale of galaxies, it behaves differently, providing the extra pull needed to explain their rapid rotations without invoking mysterious, unseen matter. At first glance, WIMPs seems elegant. It sidesteps the need for dark matter entirely, offering a simpler explanation for those stubborn galactic rotation curves. In WIMPs framework, stars on the outskirts of galaxies aren't held in place by invisible halos, they're responding to a subtle tweak in gravity's behavior. And for some galaxies, especially isolated ones with minimal dark matter influence, WIMPs predictions match observations surprisingly well. It's a compelling alternative, one that appeals to scientists who prefer Occam's razor, the principle that the simplest solution is often the best. But the universe rarely makes things easy. While WIMPs excels at explaining individual galaxies, it stumbles when faced with larger cosmic structures. Take the bullet cluster, where the separation of visible matter and gravitational lensing screams dark matter. WIMPs struggles to account for this without adding extra assumptions. Similarly, the intricate web of galaxy clusters and the precise fluctuations in the cosmic microwave background, the afterglow of the Big Bang, align almost perfectly with dark matter models. WIMPs, in contrast, requires patches and adjustments to fit these observations, losing some of its initial simplicity. The debate between dark matter and modified gravity isn't just academic, it cuts to the core of how we understand the universe. Proponents of dark matter argue that its explanatory power, backed by decades of evidence, is too vast to dismiss. They point to the countless gravitational anomalies, from galaxy rotations to lensing effects, all pointing toward an unseen mass. Detractors, however, see WIMPs as a bold correction to an over-reliance on invisible crutches. After all, science advances when we question assumptions, even the most deeply held ones. Yet the most fascinating possibility isn't that one theory is right and the other wrong, but that both might be incomplete. Could dark matter and modified gravity coexist, each explaining different pieces of the puzzle? Some researchers explore hybrid models where dark matter exists but gravity also behaves unusually at cosmic scales. Others investigate whether dark matter itself might have complex properties, interacting in ways we haven't yet imagined. What's clear is that the mystery of galactic motion refuses to surrender to easy answers. Whether it's unseen particles or rewritten laws, the solution will force us to rethink reality itself. And that's the beauty of science. It thrives not on certainty, but on the thrill of the unknown, the chase for truths just beyond our grasp. Picture the universe not as a random scattering of galaxies, but as an intricate tapestry, one woven with threads of invisible dark matter stretching across unfathomable distances. This is the cosmic web, the hidden skeleton of the cosmos, where galaxies cling like dewdrops to a spider's silk. Without dark matter's gravitational pull, this grand architecture would collapse into chaos, leaving the universe a formless void. The story begins just after the Big Bang, when the newborn universe was a seething ocean of particles and energy. Tiny quantum fluctuations, random ripples in density, created slight variations in the distribution of matter. But here's the twist: ordinary matter, battered by intense radiation, couldn't clump together effectively. Dark matter, unaffected by light or heat, began gathering in these faint ripples, amplifying them over time. Think of it like sediment slowly settling in a river. Dark matter's gravity drew more and more mass into those initial wrinkles, carving out the first tendrils of the cosmic web. As eons passed, these tendrils grew into colossal filaments, each one a river of dark matter millions of light years long. Where these filaments intersected, galaxies congregated like cities at crossroads, drawn together by the irresistible pull of gravity. The most massive intersections became galaxy clusters, dense metropolises of stars, gas, and dark matter, each one a gravitational anchor in the web. Meanwhile, the spaces between filaments remained eerily empty, vast cosmic deserts where few galaxies dared to venture. This web isn't just a static structure, it's dynamic, constantly evolving. Simulations of the universe, like the famous Illustris project, showed dark matter filaments acting as cosmic highways, funneling gas and galaxies toward clusters in an endless cycle of growth. When two clusters collide, their dark matter continues unimpeded, while ordinary matter, like the hot gas between galaxies, slows and heats up, creating shock waves visible in X-ray telescopes. These collisions are cosmic fingerprints, revealing the stark divide between the seen and the unseen. Perhaps the most astonishing evidence for this web comes from gravitational lensing maps, which trace dark matter's distribution by measuring how it bends light from distant galaxies. These maps reveal filaments so vast they defy comprehension, threads of invisible mass connecting clusters across billions of light years. Some filaments even stretch through seemingly empty voids, proving that dark matter's influence extends far beyond the galaxies we can see. Yet for all its grandeur, the cosmic web raises profound questions. Why does dark matter clump so predictably? Could its particles interact in ways we haven't yet detected, sculpting finer structures within the web? And what does this mean for the fate of the universe? One thing is certain: without dark matter's invisible hand, the cosmos would lack its breathtaking order. No galaxies, no clusters, no web, just a quiet, endless dark. Every time we map a new filament or simulate the web's growth, we're not just studying dark matter, we're reading the universe's blueprints, uncovering the hidden design behind everything we see. And as our telescopes peer deeper into the void, who knows what other secrets these invisible threads might reveal? To truly grasp how dark matter shapes the universe, we must turn to the digital cosmos, vast supercomputer simulations where scientists recreate billions of years of cosmic evolution in mere weeks. Among the most groundbreaking is the Millennium Simulation, a virtual universe so detailed it tracks over 10 billion particles of dark matter from just after the Big Bang to the present day. Running on some of the world's most powerful supercomputers, this simulation didn't just mirror the universe we see, it predicted structures astronomers hadn't yet discovered, revealing dark matter's invisible hand at work. Imagine throwing a handful of sand into a pond and watching the ripples spread outward. Now replace the sand with dark matter and the pond with the fabric of space-time itself. That's essentially what these simulations do. They let physicists play out how tiny quantum fluctuations in the early universe grew under gravity's pull into the sprawling cosmic web we observe today. The results are staggering. Virtual galaxies form in the same clusters and filaments as real ones, with dark matter's gravitational wells guiding ordinary matter like water flowing into valleys. Without dark matter in the equations, the simulated universe looks nothing like our own. Galaxies are too few, too scattered, and lack the intricate connections we see through telescopes. But the real magic happens when simulations make testable predictions. Take the distribution of satellite galaxies, smaller galaxies orbiting larger ones like the Milky Way. Early simulations suggested there should be hundreds more satellite galaxies around our own than we'd observed. At first, this seemed like a flaw in the dark matter model. Then astronomers developed more sensitive telescopes, and lo and behold, they found the missing satellites, faint and hidden but exactly where the simulations said they'd be. It was a eureka moment, proving these digital universes weren't just abstract exercises, they were roadmaps to reality. The latest simulations go even further, incorporating not just dark matter but ordinary gas, stars, and the explosive feedback from supernova and black holes. Projects like Illustris TNG and Eagle create galaxies with spiral arms, bulges, and even realistic stellar populations, all emerging naturally from the interplay of dark matter and physics. When virtual galaxies match their real counterparts down to the finest details, it's hard to deny dark matter's role. These aren't just models, they're time machines, letting us rewind the universe's history to witness how dark matter's invisible scaffolding directed every step of cosmic evolution. Yet simulations also reveal lingering puzzles. Some predict dark matter should clump more densely at galaxy centers than we observe, or that galaxies should rotate faster than they do. These discrepancies hint that dark matter might be more complex than we've assumed, perhaps interacting with itself in unseen ways, or even influenced by forces beyond gravity. Every mismatch between simulation and observation is a clue nudging scientists toward deeper truths. What's astonishing is how much these digital universes have taught us without ever leaving Earth. They've shown us where to point our telescopes, what strange phenomena to search for, and how the ghostly pull of dark matter weaves the tapestry of the cosmos. And as supercomputers grow more powerful, these simulations will only sharpen, probing the mysteries of dark matter with ever greater precision. The universe may hide its secrets well, but we're learning to build mirrors that reflect even its darkest corners. Stars on the outer edges of galaxies hold a secret one that defies the laws of physics as we know them. Picture a child spinning on a merry-go-round, gripping the bars tighter as the speed increases to avoid being flung off. Now imagine that same child letting go, yet somehow, instead of flying outward, they cling effortlessly to the spinning platform. That's precisely what happens in galaxies. According to Newton's laws, stars orbiting far from a galaxy's center should move slower, their speeds tapering off as gravity's grip weakens with distance. But when astronomers like Vera Rubin first measured these rotations decades ago, they found something astonishing. Stars at the edges were whipping around just as fast as those near the core, as if an unseen force were holding them in place. This mismatch between prediction and reality is no small quirk. It's a cosmic alarm bell. If galaxies were made only of the stars, gas, and dust we can see, their outer regions should rotate at speeds that would send stars spiraling into the void. The math simply doesn't add up unless something invisible is adding extra gravitational glue. That something is dark matter, an enormous halo of unseen mass enveloping galaxies like an invisible cocoon. Think of it as a hidden counterweight. It's gravity pulling just enough to keep those speeding stars from escaping. The greater the discrepancy between a galaxy's visible mass and its rotation speed, the more dark matter must be lurking in the shadows. The evidence doesn't stop there. Spiral galaxies, elliptical galaxies, even oddball dwarf galaxies all exhibit the same puzzling rotation curves, as if dark matter's influence is universal. Take the Andromeda Galaxy, our nearest galactic neighbor. Observations show its outer stars orbiting at nearly the same velocity as those closer in, a pattern that would require at least 10 times more mass than what's visible. Similar anomalies appear in the tiniest dwarf galaxies, where dark matter's dominance is even more extreme. Some of these faint, wispy galaxies contain so little ordinary matter that they're essentially dark matter clouds with a sprinkle of stars, their rotations entirely dictated by the invisible. What's remarkable is how elegantly dark matter solves the puzzle. Unlike alternative theories like tweaking gravity's laws, it doesn't require special rules for different galaxies. Instead, it offers a single, unifying explanation. The more mass a galaxy has, visible or not, the stronger its gravitational pull. This consistency is why rotation curves remain one of the strongest pillars of dark matter theory. Even in galaxies where visible matter is sparse, the rotation speeds point to the same conclusion: there's far more to the universe than meets the eye. Yet the mystery deepens when we ask how dark matter arranges itself to produce these perfect rotation curves. Computer simulations suggest its halos aren't just featureless blobs, but have intricate structures dense at the center and fading outward in a precise gradient. This distribution is key. Too much dark matter near the edges and galaxies would spin even faster. Too little and the outer stars would drift away. It's as if dark matter fine-tuned its own arrangement to match the observed rotations, a cosmic balancing act billions of years in the making. The implications are profound. If dark matter didn't exist, galaxies as we know them wouldn't either. Their elegant spirals, their stable orbits, even their very existence would be impossible without this invisible scaffold. Every time astronomers measure a galaxy's rotation, they're not just charting stars, they're mapping the ghostly presence that shapes the cosmos. And while the nature of dark matter remains elusive, its gravitational signature is written plainly in the stars, a silent testament to the universe's hidden depths. Computer simulations paint a vivid picture of how dark matter should shape the cosmos, especially when it comes to the swarms of small satellite galaxies orbiting larger ones like the Milky Way. These digital universes predict hundreds, even thousands of dwarf galaxies dancing around each massive host, born from the dense clumps of dark matter peppering their halos. But when astronomers peer into the night sky, they find far fewer satellites than expected. This glaring mismatch, dubbed the missing satellite problem, has become one of the most persistent puzzles in modern astrophysics, forcing scientists to question whether dark matter behaves differently on small scales than we've assumed. The roots of this mystery trace back to the earliest dark matter simulations, where researchers noticed something peculiar. As virtual galaxies formed within their dark matter halos, smaller subhalos emerged like knots in a tangled rope, each one a potential cradle for a satellite galaxy. The math suggested our Milky Way alone should host at least several hundred of these faint companions, yet for decades, astronomers had only spotted about a dozen. At first, some dismissed the discrepancy as an observational fluke. Perhaps the missing satellites were simply too dim to detect. But as telescopes grew more sensitive, revealing ultra-faint dwarfs with as few as 1,000 stars, the gap between prediction and reality stubbornly remained. One possible explanation lies in the complex interplay between dark matter and ordinary matter during galaxy formation. While dark matter's gravity draws gas inward, other forces, like supernova explosions or radiation from newborn stars, can push it back out, preventing small clumps from ever forming stars. Simulations that include these feedback effects show fewer visible satellites, as many dark matter subhalos end up dark, empty of stars but still lurking invisibly. The James Webb Space Telescope is now hunting for these starless halos by their subtle gravitational tugs on background light, probing the shadows for ghosts of galaxies that never were. Another twist comes from the properties of dark matter itself. Most models assume it's cold, slow-moving and clumpy, perfect for forming small-scale structures. But if dark matter has even a tiny amount of inherent motion, known as warmth, it could smooth out those smallest clumps, reducing the number of satellites. Alternatively, dark matter might interact with itself through unknown forces, scattering particles and eroding subhalos from within. Each scenario leaves a distinct fingerprint in the distribution of satellites we observe or fail to observe. The missing satellite problem isn't just a quirk of our local galactic neighborhood. Even in distant galaxy clusters, where thousands of galaxies mingle, the count of small satellites falls short of predictions. This cosmic pattern hints that the solution isn't about our telescope's limitations, but something fundamental in the laws governing dark matter. Whether it's unseen physics in galaxy formation or a radical revision of dark matter's nature, the answer promises to reshape our understanding of the invisible scaffolding holding up the universe. What makes this puzzle so compelling is its power to bridge the vast and the minute. It connects the grand sweep of cosmic evolution, the birth of galaxies and clusters, to the elusive behavior of individual dark matter particles. Every faint dwarf galaxy discovered, every invisible subhalo inferred, brings us closer to deciphering dark matter's hidden rules. And as simulations grow more sophisticated, weaving in everything from quantum effects to the violent births of stars, they're not just predicting the cosmos, they're challenging us to see it anew. After all, the greatest mysteries often lie not in what we observe, but in what we expect to find and somehow can't. In the earliest moments of the universe, before the first stars flickered to life, dark matter was already at work, quietly sculpting the cosmos from the shadows. Picture a newborn universe just a few 100 million years old, still cooling from the heat of the Big Bang. Ordinary matter, a chaotic soup of protons and electrons, was too energetic to clump together, constantly buffeted by intense radiation. But dark matter, indifferent to light's push and pull, began gathering in faint ripples under gravity's patient influence. These ripples became the universe's first blueprints, the gravitational wells where gas could eventually settle and ignite into stars. Without dark matter's invisible scaffolding, the cosmic dawn might never have broken. The process was delicate yet relentless. As dark matter's tendrils grew denser, they created a gravitational tug strong enough to overcome the radiation pressure fighting against ordinary matter. Gas clouds drawn into these invisible wells began to cool and fragment, collapsing into the first protogalaxies, small, faint structures barely a fraction of our Milky Way's mass. Simulations of this epoch show dark matter acting like a cosmic sieve, channeling gas into ever tighter knots until the pressure and temperature at their cores sparked nuclear fusion. The result, population 3 stars, the universe's very first stellar generation. These stars were unlike anything we see today, monstrously massive, short-lived, and made purely of hydrogen and helium. Their explosive death seeded the cosmos with heavier elements, paving the way for the diverse galaxies that followed. What's astonishing is how precisely dark matter's distribution had to align for this process to unfold. Too much clustering and gas would have collapsed too quickly, creating black holes instead of stars. Too little, and the universe might have remained a dark, starless void for billions of years longer. The timing was equally critical. Recent observations from the James Webb Space Telescope have revealed galaxies forming earlier than many models predicted. suggesting dark matter's gravitational pull was even more efficient than we thought. These ancient galaxies, glimpsed as they were over 13 billion years ago, shouldn't have had time to grow so large unless dark matter's invisible hand guided their assembly with extraordinary speed. But dark matter didn't just kickstart star formation, it dictated the very architecture of the early universe. The same filaments and knots we see in today's cosmic web were already taking shape, with dark matter's gravity funneling gas along invisible highways. Where these filaments crossed, the first quasars flared to life, their supermassive black holes growing at a pace that still baffles astronomers. How did these behemoths form so quickly? The answer may lie in dark matter's ability to create deep, dense wells where gas could accumulate rapidly, feeding black holes like nothing we see in the modern universe. Yet for all its influence, dark matter remains frustratingly indirect in this epoch. Unlike later eras, where its effects are written plainly in galaxy rotations or lensing maps, the early universe offers only whispers, anomalies in the cosmic microwave background, unexpected brightness in primordial galaxies, or puzzling gaps in the timeline of reionization. Each clue is a piece of a jigsaw puzzle we're still assembling, one that might reveal not just how dark matter shaped the past, but how it continues to shape the universe's future. The cosmic dawn wasn't just a transition from darkness to light. It was the moment dark matter proved its mastery over the cosmos. Without its unseen guidance, the stars we admire, the galaxies we map, even the atoms that make up our bodies might never have existed. And as we peer deeper into those first flickers of starlight, we're not just exploring the past, we're deciphering the hidden rules that govern everything. While WIMP and axions dominate the dark matter conversation, the universe rarely settles for simple answers. Scientists have proposed a host of other candidates, each more exotic than the last, stretching our understanding of physics to its limits. Take sterile neutrinos, hypothetical cousins to the familiar neutrinos that stream through our bodies by the trillions every second. Unlike ordinary neutrinos, which interact via the weak nuclear force, sterile neutrinos would feel only gravity, making them nearly impossible to detect directly. Yet their subtle influence might explain more than just dark matter. Some models suggest these elusive particles could be responsible for mysterious X-ray signals detected from distant galaxies, emissions that ordinary matter can't account for. Then there's the possibility that dark matter isn't a particle at all, but a cosmic relic from the universe's violent infancy, primordial black holes. These aren't the black holes formed from collapsing stars. They'd be far older, forged in the extreme density of the Big Bang itself. Ranging in size from a speck of dust to a small moon, they'd drift through space unseen, their gravity the only trace of their existence. The idea gained traction when gravitational wave detectors picked up mergers of black holes with puzzling masses, ones that don't fit neatly into our models of stellar evolution. Could these be primordial black holes hiding in plain sight? The challenge is proving it. Unlike particle dark matter, these black holes would leave no trails in underground detectors, only fleeting distortions in starlight or unexpected ripples in spacetime. Perhaps the most mind-bending candidates emerge from theories beyond our familiar four dimensions. String theory, for instance, suggests extra spatial dimensions curled into shapes too tiny to perceive. Within these hidden folds, entirely new particles could exist, heavy, slow-moving, and oblivious to the forces that govern our world. These Kaluza-Klein particles, as they're called, would appear to us as dark matter, their gravity leaking into our dimensions while their other interactions remain locked away. Detecting them would require experiments sensitive not just to new particles, but to the very fabric of higher dimensional space itself. the diversity of these theories reveals just how wide open the dark matter puzzle remains. Every candidate, whether sterile neutrino, primordial black hole, or extra-dimensional visitor, comes with its own set of challenges. Some might interact too weakly to ever detect. Others could blend seamlessly with known astrophysical phenomena hiding in the noise. Yet each possibility pushes science forward, forcing us to build better detectors, refine our models, and question long-held assumptions. What's remarkable is how these ideas aren't just about dark matter. They're gateways to deeper mysteries. Sterile neutrinos could reshape our understanding of particle physics. Primordial black holes might offer a window into the universe's first moments. And extra-dimensional particles could unveil realms beyond our perception. The search for dark matter isn't just about finding what's missing. It's about discovering how much more there is to know. Every dead end, every unexpected clue, reminds us that the cosmos still holds secrets we've only begun to imagine. Detecting dark matter is like trying to catch smoke with your bare hands. You know it's there, you can see its effects, but the moment you reach out, it slips through your fingers. Scientists have spent decades building increasingly sensitive experiments, yet every detection claim has evaporated under scrutiny, leaving behind only tantalizing hints and frustrating dead ends. The challenge isn't just that dark matter refuses to interact with ordinary matter. It's that the universe is drowning in a sea of background noise, masking any faint signal dark matter might produce. Take the case of underground detectors, like those buried deep beneath mountains to shield them from cosmic rays. These ultra-sensitive instruments wait for the rare moment a dark matter particle might bump into an atomic nucleus, producing a tiny flash of light or a minuscule charge. But here's the catch. Even in these pristine environments, natural radioactivity from the surrounding rock or even from the detector materials themselves can mimic the expected signal. It's like listening for a whisper in a thunderstorm. Every false alarm forces researchers to recalibrate, to dig deeper, to build ever more shielded labs. The most advanced detectors now sit in former gold mines or under Antarctic ice, where Earth itself acts as a filter against interference. Then there's the problem of scale. If dark matter interacts as weakly as theories suggest, a detector the size of a swimming pool might only see a handful of events per century. To compensate, experiments have grown massive, some filled with tons of liquid xenon or argon, hoping to increase the odds of a fleeting interaction. But even these behemoths have come up empty, pushing the limits of how faint an interaction we can realistically measure. The latest generation of detectors, like Lux Zeppelin and Xeno NNT, are so sensitive they could spot a single dark matter particle colliding with an atom. Yet the silence persists, forcing scientists to ask, are we looking for the right thing, or are we missing something fundamental? The hunt grows even trickier when we consider dark matter's possible properties. If it's not a WIMP or an action but something entirely unexpected, a particle that interacts through an unknown force, or one that's far lighter or heavier than predicted, our current experiments might be blind to it. Some theories suggest dark matter could be fuzzy, spread out like a wave rather than a discrete particle, or that it might cluster in ways that evade our detectors. Others propose it could decay over time, leaving behind traces too subtle for our instruments to catch. Every null result narrows the possibilities, but it also fuels new ideas, sending physicists back to the drawing board with ever more creative solutions. Perhaps the most humbling realization is that dark matter might simply not want to be found. Unlike other cosmic mysteries, which eventually yielded to relentless observation, black holes, once purely theoretical, now photographed, gravitational waves, once Einstein's speculation, now routinely detected, dark matter resists every tool we throw at it. Telescopes can't see it, colliders can't produce it, detectors can't catch it, yet its gravitational fingerprints are everywhere, from the spin of galaxies to the bend of light around empty space. This paradox, knowing dark matter exists while being utterly unable to touch it, is what makes the search so maddening and so thrilling. What keeps scientists going is the certainty that the breakthrough, when it comes, will rewrite physics. Whether it's a new particle, a hidden dimension, or a flaw in our understanding of gravity, the answer won't just solve the dark matter puzzle. It will open doors to realms of knowledge we can't yet imagine. Until then, the hunt continues, a testament to human curiosity's power to chase even the most elusive truths. One of the most striking demonstrations of dark matter's existence comes from the chaos of colliding galaxies, cosmic car crashes where the invisible suddenly leaves its mark. The Bullet Cluster stands as the ultimate case study, a pair of galaxy clusters that slammed into each other at millions of miles per hour, creating a perfect natural experiment. Here's the twist. While the galaxies themselves pass through one another largely unscathed, their stars so far apart that collisions are rare, the hot gas between them, detectable by its X-ray emissions, piled up like cosmic traffic jam. But the real revelation came when astronomers mapped the cluster's gravity using gravitational lensing. The distortion of background galaxies revealed something astonishing. The bulk of the mass wasn't where the gas glowed brightest. Instead, it had sailed ahead, completely divorced from the visible matter. This separation is like watching oil and water unmix in slow motion. The gas, made of ordinary matter, interacts electromagnetically, slowed by friction as the clusters collided. But dark matter, indifferent to these forces, plowed straight through, carrying the bulk of the gravitational influence with it. The result, two distinct fingerprints, X-rays marking the gas's location, and gravitational lensing revealing dark matter's invisible wake. It's as if someone shook a snow globe and the glitter settled in one spot while the water moved to another, except here, the glitter is the mass shaping the cosmos. The Bullet Cluster isn't alone. Similar separations appear in other merging systems, like the Musket Ball Cluster or Abell 528. Each one reinforces the same conclusion. Dark matter isn't just an abstract idea, it's a physical substance that behaves differently from anything we can see. These collisions also rule out alternative theories like modified gravity, which struggle to explain why the gravitational pull wouldn't align with the visible mass. If gravity worked differently on large scales, Asmund suggests, the lensing effect should trace the gas, not wander off on its own. Yet in every observed collision, gravity follows the dark matter, not the stars or gas. What makes these observations so powerful is their simplicity. Unlike particle detectors or theoretical models, galaxy collisions offer a direct, visual test of dark matter's properties. They show us how it moves, how it clusters, and crucially, how little it cares about the ordinary matter we're made of. These aren't just shadows on the wall of Plato's cave. They're the footprints of something real, something massive, something utterly unlike anything we've ever touched. Yet the Bullet Cluster also raises new questions. Why does dark matter seem so perfectly collisionless? Could there be a tiny interaction we haven't detected? Or does it truly ignore everything except gravity? Future observations of even more violent cosmic smash-ups like the train wreck collision of El Gordo, a cluster 7 billion light-years away, may hold the answers. Every collision is a snapshot of dark matter's behavior, a frame in a cosmic film we're only beginning to watch, and as our telescopes grow sharper, who knows what other secrets these chaotic encounters will reveal. The search for dark matter is entering its most thrilling chapter yet, with a new generation of tools poised to peel back the universe's best-kept secret. Leading the charge is the Vera C, Rubin Observatory, a revolutionary telescope perched high in Chile's Atacama Desert. When it begins its decade-long legacy survey of space and time in 2025, it won't just scan the sky, it'll dissect it, capturing panoramic images so detailed they could spot a golf ball on the moon. But here's the real game changer. By tracking billions of galaxies and their gravitational distortions with unprecedented precision, Rubin could map dark matter's invisible web across a quarter of the visible universe. Imagine tracing the outline of a shadow by watching how it bends the light around it. That's the power of this experiment, revealing dark matter's structure in ways we've only dreamed of. Meanwhile, deep underground, detectors are reaching sensitivities that border on the surreal. The LUX Zeppelin experiment, nestled nearly a mile beneath South Dakota's Black Hills, now holds 10 metric tons of liquid xenon in its quest to catch a dark matter particle's faint whisper. Its predecessor, LUX, ruled out entire classes of potential particles. This upgraded version could finally stumble upon the real thing. Across the globe, similar experiments, from Italy's Zeno NNT to China's Panda X, are turning Earth itself into a cosmic net, each one probing different slices of dark matter's possible properties. The strategy is simple: cast as wide a net as possible, because we still don't know if dark matter is heavy or light, fast or slow, or whether it interacts in ways we haven't even considered. But telescopes and underground labs are just part of the story. Particle colliders like the Large Hadron Collider are staging their own hunt, smashing protons together at near light speeds in hopes of creating dark matter in the debris. While we wouldn't see the particles directly, their presence could be inferred from missing energy, a telltale gap in the collision's aftermath. It's like listening for silence in a symphony, where the absence of sound reveals as much as the notes themselves. And then there's the space-based approach. NASA's upcoming Nancy Grace Roman Space Telescope will join ESA's Euclid in creating 3D dark matter maps by measuring how light bends across cosmic distances. Together, these missions could settle whether dark matter is cold, warm, or something even stranger. What makes this era so electrifying is the sheer diversity of approaches. If dark matter refuses to show up in one experiment, another might catch it off guard. Perhaps it's not a single particle but a family, or maybe it interacts through forces beyond our current physics. Some theorists even suggest we're on the verge of a Copernican-scale revolution, realizing that dark matter isn't just a substance but a signpost pointing to entirely new laws of nature. Every null result, every unexpected blip in the data tightens the noose around this mystery. The stakes couldn't be higher. Solving dark matter wouldn't just fill a gap in our equations. It would rewrite the story of cosmic evolution, from the first stars to the fate of galaxies. It might even answer why we exist at all in a universe that seems fine-tuned for life. As these experiments come online, we're not just building better tools, we're crafting keys to unlock the universe's deepest vault. And if history is any guide, the greatest discoveries often come from where we least expect them. Dark matter doesn't just shape the universe as we know it, it holds the keys to the cosmos' ultimate fate. Whether the universe continues expanding indefinitely, collapses back on itself in a fiery crunch, or reaches some delicate equilibrium hinges on the invisible tug of this enigmatic substance. It's a cosmic balancing act where the gravitational pull of dark matter fights against the relentless push of dark energy, the mysterious force accelerating the universe's expansion. The outcome of this struggle will determine whether galaxies drift apart forever or whether gravity might one day regain the upper hand. To grasp this cosmic drama, picture a pendulum swinging in slow motion. On one side, dark matter's gravity acts as the weight pulling the universe toward contraction. On the other, dark energy is the force pushing the pendulum outward, stretching space itself. The balance between these two dictates whether the pendulum eventually reverses direction or swings endlessly outward. Right now, observations suggest dark energy is winning. The universe's expansion is speeding up, with galaxies fleeing from one another faster every second. But dark matter's role isn't passive. Its gravitational influence still shapes how quickly structures like galaxies and clusters form, which in turn affects how dark energy's push plays out across cosmic time. Here's where things get even more intriguing. The amount and behavior of dark matter could change the entire equation. If dark matter interacts with itself in ways we haven't yet detected, perhaps through some hidden force, it might clump differently over time, altering the gravitational landscape. Some theories even suggest dark matter could decay, slowly releasing energy that might counteract dark energy's expansion. Alternatively, if dark matter is more abundant than current estimates, its cumulative gravity might one day halt and reverse the universe's expansion, leading to a big crunch where everything collapses back into a singularity. The cosmic microwave background, the faint afterglow of the Big Bang, offers tantalizing clues. Tiny fluctuations in this ancient light reveal how matter, both visible and dark, was distributed in the early universe. By studying these patterns, scientists can extrapolate how dark matter's gravitational pull has shaped the cosmos over billions of years and project its influence far into the future. Current data favors a universe that keeps expanding, growing colder and darker as galaxies vanish beyond the observable horizon. But without fully understanding dark matter's properties, these predictions remain uncertain. What's at stake isn't just an academic curiosity. The fate of the universe hinges on the interplay between forces we're only beginning to comprehend. If dark matter's grip weakens over time, galaxies might dissolve into the void, leaving behind a desolate, empty cosmos. If it strengthens, the universe could face a violent end, collapsing in on itself in a reversal of the Big Bang. Or perhaps there's a middle path, a scenario where expansion slows but never stops, leaving the universe in a state of perpetual equilibrium. This is why unlocking dark matter's secrets isn't just about solving a scientific puzzle. It's about glimpsing the ultimate destiny of everything. Every experiment, from underground detectors to space telescopes, brings us closer to answering one of humanity's oldest questions. How does the story of the universe end? And while we might not live to see that final chapter, the search itself reveals just how deeply interconnected we are with the invisible forces weaving the cosmos together. The more we learn about dark matter, the more we realize it's not just a hidden component of the universe, it's the architect of its future. One of the biggest misconceptions about dark matter is that it's just empty space, a fancy term scientists use to describe cosmic nothingness. But nothing could be further from the truth. Dark matter isn't the absence of matter. It's a real, physical substance with measurable gravitational effects that shape the entire universe. Think of it like the wind. You can't see it, but you can see the leaves it moves, the waves it stirs, the way it bends trees to its will. Dark matter works the same way, invisible yet undeniable in its influence. Another common myth is that dark matter is merely a placeholder, a temporary gap in our knowledge that will eventually be replaced by a better theory. While it's true that science evolves, dark matter isn't some vague idea tossed out to cover up ignorance. It's a conclusion drawn from decades of rigorous observation, from the way galaxies rotate to how light bends around galaxy clusters. These aren't guesses, they're reproducible, measurable phenomena that all point to the same unavoidable truth: something massive is out there, and it's not anything we've seen before. The evidence is so overwhelming that dismissing dark matter would be like insisting gravity doesn't exist just because we can't see the force itself. Then there's the belief that dark matter must be exotic or magical because it doesn't interact with light. But invisibility doesn't make something supernatural. Neutrinos, for example, are real particles that stream through your body by the trillions every second without you ever noticing. They barely interact with matter, yet no one calls them imaginary. Dark matter is similar, just another piece of the universe's puzzle, obeying physical laws even if we haven't fully mapped them yet. Perhaps the most persistent misunderstanding is the idea that dark matter is rare or insignificant, lurking only in the distant corners of space. In reality, it's everywhere, far more abundant than the atoms making up stars, planets, and even our own bodies. For every particle of visible matter, there's roughly 5 times as much dark matter woven through the cosmos. You're swimming in it right now, with countless dark matter particles passing through you every second, harmless, undetectable, yet fundamentally shaping the universe around you. Clearing up these myths isn't just about setting the record straight, it's about opening doors to wonder. When people realize dark matter isn't science fiction but a real, tangible mystery waiting to be solved, it transforms the way they see the night sky. Suddenly, those glittering galaxies aren't just pretty lights, they're clues to a deeper story, one where most of the universe remains hidden in plain sight. And that's what makes astrophysics so thrilling, not just the answers we have, but the questions that keep us reaching further into the dark. If dark matter is the cosmic glue holding galaxies together, dark energy is the mysterious force ripping them apart, an invisible pressure stretching the very fabric of space itself. Picture the universe as a balloon expanding not just steadily, but faster every second, with galaxies pinned to its surface racing away from one another at speeds that defy gravity's pull. This startling discovery, made in the late 1990s by observing distant supernova, revealed that something far stranger than dark matter was at work, a repulsive force we now call dark energy. Together, these two unseen phenomena dominate the cosmos, with dark matter sculpting its structure and dark energy dictating its ultimate fate. What makes their interplay so fascinating is how perfectly opposed they seem. Dark matter's gravity binds galaxies into clusters and weaves the cosmic web, while dark energy pushes that web apart, accelerating the universe's expansion against gravity's relentless tug. It's as if the cosmos is caught in a tug of war between two invisible giants, one building, the other dismantling. Yet for all their opposition, they're deeply connected, together accounting for 95% of the universe's total mass energy. The ordinary matter we see, stars, planets, nebulae, is just the faintest shimmer on the surface of a much darker, stranger reality. The origins of dark energy are even more perplexing than dark matter's. Einstein's cosmological constant, once dismissed as his greatest blunder, has resurfaced as a leading explanation, a property of space itself that generates repulsive gravity as the universe expands. Alternatively, dark energy might stem from a dynamic field permeating the cosmos, akin to the inflationary field that propelled the Big Bang. Some theories even suggest it's linked to extra dimensions or quantum vacuum fluctuations. But unlike dark matter, whose gravitational fingerprints are everywhere, dark energy's effects only become obvious on the largest scales, making it even harder to study. This duality, dark matter's local pull versus dark energy's global push, creates a delicate balance that shapes cosmic evolution. In the early universe, dark matter's gravity dominated, allowing galaxies and clusters to form. But around 5 billion years ago, dark energy's influence surged as the universe grew larger and more diffuse, initiating the accelerated expansion we see today. The timing was eerily precise. Had dark energy emerged earlier, galaxies might never have coalesced. Later, and the cosmos could have collapsed before life arose. It's as if the universe followed a hidden script, with dark matter and dark energy playing their parts at just the right moments. Yet the most unsettling possibility is that dark energy isn't constant but evolving. If it strengthens over time, it could tear apart galaxies, stars, and even atoms in a catastrophic Big Rip. If it weakens, gravity might regain control, reversing the expansion. Or perhaps the balance will hold, leaving the universe to expand forever into cold, silent darkness. The answer lies in measuring the expansion rate with ever greater precision, a task for observatories like the James Webb Space Telescope and the upcoming Euclid mission. What's certain is that dark matter and dark energy aren't just footnotes in cosmology. They're the main characters in the universe's story. Unraveling their mysteries won't just tell us why galaxies spin too fast or space expands too quickly. It will reveal why the cosmos looks the way it does and what destiny awaits it billions of years from now. The deeper we probe, the clearer it becomes. We're only beginning to read the universe's darkest chapters. Dark matter's enigmatic nature hasn't just baffled scientists, it's ignited the imaginations of storytellers, weaving its way into the fabric of popular culture as one of the most compelling mysteries of our time. From the pages of science fiction novels to the sprawling visuals of blockbuster films, dark matter has become a cosmic Rorschach test, a blank canvas for humanity's wildest theories and fears. Take Philip Pullman's His Dark Materials trilogy, where dust, a mysterious, invisible particle, mirrors the real-world puzzle of dark matter, embodying both scientific curiosity and metaphysical wonder. Or consider Interstellar, where the unseen gravitational forces distorting space-time echo the very real influence of dark matter on galactic structures. These stories don't just entertain, they reframe complex science into emotional narratives, letting audiences feel the mystery rather than just study it. Hollywood, in particular, loves dark matter for its dramatic potential. In Marvel's Agents of S.H.I.E.L.D., it's a volatile energy source threatening entire worlds, while Star Trek treats it as a hazardous anomaly warping the fabric of reality. Even video games like Destiny build entire mythologies around it, casting dark matter as a primordial force tied to the birth and death of civilizations. What makes these portrayals so gripping is how they tap into the same awe that drives real scientific inquiry, the thrill of confronting the unknown. Yet they also reveal a cultural tension. Dark matter is often depicted as dangerous or unstable, a trope rooted in our instinctive fear of what we can't see or control. But pop culture doesn't just dramatize dark matter, it democratizes it. When the Big Bang Theory cracks jokes about WIMP or Doctor Who weaponizes it as the last breath of the universe, these moments plant seeds of curiosity in millions of viewers who might never pick up an astrophysics paper. They turn abstract equations into relatable metaphors, sparking questions like could dark matter be harnessed? Or what if it's alive? Questions scientists themselves entertain in speculative research. Even music and art have embraced the theme, with bands like Muse naming albums the second law, unsustainable after thermodynamic principles entangled with cosmic mysteries, and digital artists rendering dark matter as swirling, ghostly tendrils in visionary installations. The irony is delicious. While dark matter refuses to reveal itself in labs, it thrives in the collective imagination, evolving from scientific hypothesis to cultural icon. It's a reminder that some of humanity's greatest discoveries begin not with data, but with wonder, the same wonder that drives a child to stare at the stars and ask what's out there. Whether as a plot device or a philosophical muse, dark matter bridges the gap between the rigor of science and the boundless creativity of storytelling. And perhaps that's its greatest power, not just shaping galaxies, but shaping how we dream about them. The pursuit of dark matter isn't just a scientific challenge, it's an ethical balancing act, demanding careful consideration of how we allocate resources, collaborate across borders, and weigh the consequences of discovery. Consider the staggering investments. Particle colliders like the Large Hadron Collider cost billions to build and operate, while underground detectors require years of meticulous construction. These projects compete for funding with pressing global needs: climate research, medical advancements, poverty alleviation. Yet the potential payoff is equally profound. Unlocking dark matter's secrets could revolutionize our understanding of gravity, energy, even the birth of the universe itself. The ethical question isn't whether to pursue this knowledge, but how to balance it against other urgent priorities, ensuring scientific progress doesn't come at the expense of societal good. International collaboration adds another layer of complexity. Dark matter research thrives on shared data, from gravitational lensing maps to neutrino observatories spread across continents. But geopolitical tensions can strain these partnerships as nations vie for credit or restrict access to critical facilities. The ethical tightrope lies in fostering open science while respecting national interests and security concerns. Take the case of China's Panda X experiment or Japan's Super Kamiok and detector. Their breakthroughs benefit humanity, yet the competitive race for first discovery risks fragmenting the very cooperation that accelerates progress. The ideal, a framework where knowledge flows freely, but contributions are recognized equitably, ensuring no single country or institution monopolizes the fruits of collective effort. Then there's the question of unintended consequences. What if dark matter research inadvertently unlocks technologies with dual uses, energy sources that could power cities or weapons? History warns us, nuclear physics gave us both clean energy and atomic bombs. While dark matter's practical applications remain speculative, the ethical imperative is clear: anticipate risks early and establish safeguards. Some theorists even ponder existential risks. Could experiments probing dark matter's properties accidentally destabilize the fabric of space-time? The odds are vanishingly small, but the mere possibility demands rigorous oversight, blending bold curiosity with humility. Perhaps the deepest ethical consideration is one of perspective. In a world grappling with inequality and conflict, does studying an invisible cosmic substance seem indulgent? The counterargument is equally compelling. Dark matter research epitomizes humanity's shared quest for understanding, transcending borders and ideologies. It reminds us that we're part of something vast, fostering unity in curiosity. The challenge lies in articulating this value to skeptics, not as abstract idealism, but as a catalyst for innovation, inspiration, and long-term survival. After all, every major leap in science began as a seemingly impractical pursuit. The stars have always called us to look beyond immediacy, and dark matter is no exception. Ultimately, the ethics of this endeavor hinge on transparency and inclusivity, ensuring the search for dark matter isn't just a technical feat, but a collective human project. From involving diverse voices in funding decisions to educating the public on why this invisible mystery matters, the goal is to make the cosmos accessible to all. Because if dark matter truly shapes the universe, then understanding it isn't just science, it's stewardship, and that's a responsibility we all share. Walking into a planetarium, you're immediately surrounded by the cosmos, stars flickering to life on the dome above, galaxies swirling in vivid detail. But what about the parts of the universe we can't see? That's where museums and science centers step in. transforming abstract concepts like dark matter into tangible, awe-inspiring experiences. Take the American Museum of Natural History's immersive Dark Universe show, narrated by Neil deGrasse Tyson. Visitors don't just hear about dark matter, they watch it ripple through a simulated cosmic web, its gravitational tendrils tugging galaxies into place like invisible puppet strings. These visualizations aren't just eye candy, they're bridges between cutting-edge research and public understanding, turning mathematical abstractions into stories anyone can grasp. Online platforms have amplified this outreach, democratizing access to cosmic mysteries. YouTube channels like PBS Space Time and Kurzgesagt break down dark matter with animations so intuitive, they make the incomprehensible feel familiar. One viral video compares dark matter halos to a spider's web, where galaxies are dewdrops suspended by silken threads too fine to see. Others use relatable analogies, like imagining dark matter as a crowd of silent dancers in a pitch-black ballroom, their movements revealed only by how they bump into the visible stars. These creative approaches matter because they don't just inform, they ignite curiosity, inviting viewers to join the scientific conversation rather than spectate from the sidelines. Hands-on exhibits take the experience even further. At Chicago's Adler Planetarium, visitors manipulate interactive models to feel how dark matter's gravity bends light, dragging virtual stars across a screen with their fingertips. In Berlin's Science Center Spectrum, a mirrored installation reflects laser beams to simulate gravitational lensing, making the invisible suddenly visible. These exhibits thrive on a simple truth. People learn best when they're actively engaged, not passively lectured. By turning dark matter into something visitors can play with, literally, museums dissolve the barrier between complex theory and everyday intuition. Yet the real magic happens when outreach sparks unexpected connections. A teenager watching a planetarium show might later code a dark matter simulation for a science fair. A teacher borrowing classroom kits from NASA could inspire students to pursue astrophysics. Even social media plays a role. TikTok creators using glitter jars to explain dark matter's distribution proves science communication isn't confined to textbooks. The goal isn't just to explain dark matter, but to make it feel personal, showing how this invisible force shapes everything from the galaxies above to the atoms in our bodies. The challenge, of course, is accuracy. Simplifying dark matter for broad audiences risks distorting the science, trading nuance for accessibility. That's why leading institutions collaborate directly with researchers, ensuring every analogy, every visualization stays grounded in real data. When the European Space Agency released its Euclid Mission Toolkit for educators, it included raw telescope images alongside classroom activities, letting students analyze the same gravitational lensing patterns as professional astronomers. This balance between clarity and precision is what turns casual interest into genuine understanding. In the end, dark matter outreach isn't just about filling knowledge gaps. It's about fostering a sense of shared discovery, reminding us that the universe's greatest mysteries belong to everyone. Whether through a planetarium's dazzling visuals or a viral video's clever metaphor, these efforts prove science isn't a walled garden, it's an open invitation to look up, wonder, and ask, what else is out there? And sometimes the most profound answers begin not with a telescope, but with a spark of imagination. The idea of harnessing dark matter might sound like science fiction, but the potential applications could rewrite the rules of technology as we know it. Picture a spacecraft propelled not by burning fuel, but by tapping into the gravitational pull of dark matter, a cosmic fuel source invisible yet omnipresent. Or imagine energy grids drawing power from particles that pass effortlessly through walls, eliminating the need for finite resources like coal or uranium. These possibilities are speculative, yes, but they're rooted in the very real properties of dark matter, its abundance, its gravitational dominance, and its uncharted interactions with the known universe. While we're far from turning these concepts into reality, the mere prospect underscores why unlocking dark matter's secrets isn't just about solving a cosmic puzzle, it's about opening doors to revolutions we can barely envision. Take propulsion, for instance. Conventional rockets are shackled by the tyranny of fuel. The more you carry, the more you need to burn just to move the extra weight. But dark matter's gravitational influence could offer a way around this bottleneck. If we could somehow manipulate its pull, spacecraft might ride dark matter's gravitational currents like a sailboat catching the wind, enabling journeys across interstellar distances without the need for massive fuel reserves. Theoretical models even suggest that dark matter's distribution could create natural gravity highways in space, regions where its density bends space-time in ways that reduce travel time. It's a far cry from warp drives, but it's grounded in the same principle, leveraging the universe's hidden structures to transcend our technological limits. Then there's energy. Dark matter's sheer mass outweighing visible matter 5-to-1 means it's a staggering reservoir of gravitational potential. While we can't mine it like coal or split it like atoms, its pervasive presence hints at untapped possibilities. Some theorists speculate that if dark matter particles occasionally annihilate upon collision, as certain models predict, they could release bursts of energy detectable as faint radiation. Harnessing that energy, however fleeting or diffuse, might one day offer a power source unbound by terrestrial constraints. Even more radical is the idea of quantum computing using dark matter's properties. If dark matter interacts weakly with ordinary matter, it could serve as a near-perfect medium for qubits, isolated from the environmental noise that plagues current quantum systems. Of course, these ideas come with colossal caveats. We don't yet know if dark matter can be manipulated, concentrated, or even detected in a way that's practical for human use. Its very nature elusive, non-interacting, and pervasive makes it a maddening target for engineers. But history shows that today's scientific curiosities often become tomorrow's breakthroughs. Electromagnetism was once a laboratory oddity, nuclear fission a theoretical footnote. Dark matter could follow the same arc, transforming from cosmic enigma to technological cornerstone. What makes these possibilities so compelling isn't just their scale, it's their inevitability. The moment we truly understand dark matter, the leap from theory to application could happen faster than we expect. After all, the universe has already built the infrastructure. We just need to learn how to plug into it. Whether it's powering cities or propelling starships, dark matter's potential reminds us that the greatest discoveries aren't just about answering questions, they're about unlocking futures we've yet to dream of. Dark matter's mystery is too vast for any single field to crack alone. It demands a symphony of minds, each bringing their own tools and perspectives to the table. Physicists probe the quantum realm, designing detectors to catch elusive particles. Astronomers map the cosmos, tracing dark matter's gravitational fingerprints across galaxies. Philosophers even weigh in, questioning how our very definitions of matter and reality might need rethinking. This interdisciplinary dance isn't just helpful, it's essential. Like detectives piecing together a crime from scattered clues, each field uncovers a fragment of the truth, and only by combining them can we see the full picture. Consider how particle physics collides with astrophysics in the hunt for WIMP. Underground labs like Italy's Gran Sasso use ultra-sensitive equipment to spot rare collisions between dark matter particles and ordinary atoms. Meanwhile, telescopes like Hubble and JWST observe how dark matter bends light, providing independent evidence of its distribution. When these two approaches converge, when a lab detection aligns with astronomical observations, the case for a particular dark matter candidate grows stronger. It's a classic example of cross-validation, where disparate methods reinforce each other's findings. Without this synergy, we'd risk chasing phantoms, mistaking statistical noise for breakthroughs. But the collaboration goes beyond hard science. Computer scientists build simulations that recreate the universe's evolution, testing how hypothetical dark matter particles behave over billions of years. These digital cosmos, running on some of the world's most powerful supercomputers, allow researchers to tweak variables like particle mass or interaction strength, then compare the results to real-world observations. When a simulation produces galaxies that match what we see, like the Milky Way's rotation curve or the bullet cluster's mass separation, it's a vote of confidence for that model. The process is iterative, with each failed simulation narrowing the possibilities, guiding theorists toward better hypotheses. Even philosophers play a surprising role. Dark matter challenges foundational assumptions about the universe's composition, forcing us to confront the limits of empiricism. If a substance can dominate the cosmos yet resist detection, what does that say about our ability to comprehend reality? Philosophers of science help frame these questions, ensuring the pursuit of dark matter remains grounded in rigorous epistemology. They remind scientists that sometimes the biggest breakthroughs come from questioning the questions themselves. This multidisciplinary approach isn't without friction. Different fields speak different languages literally. A particle physicist's cross-section isn't an astronomer's angular diameter, and a philosopher's ontological commitment might baffle both. Bridging these gaps requires patience and translation, often in collaborative hubs like CERN or the Kavli Institutes, where coffee breaks spark as many ideas as formal meetings. Yet the tensions are generative, pushing each discipline to clarify its assumptions and refine its methods. The stakes couldn't be higher. Dark matter isn't just a puzzle for academics. Its resolution could redefine technology, energy, even our place in the cosmos. By pooling expertise from quantum mechanics to cosmology to logic, we're not just solving a mystery, we're rewriting the playbook for how science tackles the universe's grandest challenges. And in that collaborative spirit, the next breakthrough might come from anywhere: a lab, a telescope, or even a philosopher's thought experiment. The only wrong approach is working alone. Dark matter's refusal to reveal itself in labs is one of the most frustrating and fascinating paradoxes in modern science. We see its gravitational fingerprints everywhere, from the spin of galaxies to the bend of light around cosmic voids, yet every attempt to catch it directly has come up empty. Why? The answer might lie in the very nature of dark matter itself. If it's a particle, as many theories suggest, it could be interacting with ordinary matter so weakly that our detectors simply aren't sensitive enough yet. Imagine trying to catch a whisper in a hurricane. Even our most advanced instruments might be missing signals drowned out by cosmic noise or mundane background radiation. But the mystery deepens when we consider alternatives. What if dark matter isn't a single particle but a family of them, each with different properties? Some could be heavy and slow, like WIMP, while others are feather-light, like axions. Others still might interact through forces beyond the four we know: gravity, electromagnetism, and the strong and weak nuclear forces. This dark sector could be as complex as the visible universe, with its own rules and particles, forever hidden from our current tools. It's like realizing the ocean you've been studying isn't just water but layers of invisible currents, each moving to its own rhythm. Then there's the radical possibility that dark matter isn't particulate at all. Some theorists propose it could be a quantum field, a fluid-like substance permeating space, or even a topological defect in the fabric of the universe, a cosmic knot left over from the Big Bang. These ideas push the boundaries of physics, suggesting that dark matter's elusiveness isn't a failure of our experiments but a clue that we're missing something fundamental about how reality works. The lack of detection hasn't deterred scientists, it's fueled creativity. Experiments are now probing uncharted territories, from searching for ultra-light axions with resonant cavities to hunting for subtle distortions in ancient starlight caused by primordial black holes. Others are re-examining old data for overlooked anomalies, like faint X-ray emissions that could hint at sterile neutrinos decaying in distant galaxies. Every null result, every dead end, tightens the constraints, narrowing the possibilities like a cosmic game of 20 questions. What keeps researchers going is the certainty that the answer, when it comes, will rewrite the textbooks. Dark matter's stubborn invisibility isn't a wall. It's a mirror reflecting back the limits of our current understanding. And just as the discovery of the neutrino once seemed impossible until it wasn't, the breakthrough with dark matter might be waiting in the next experiment, the next observation, the next bold idea. Until then, the hunt continues not just for a particle, but for a whole new way to see the universe. Could dark matter be the cosmic glue connecting our universe to others? The multiverse theory, once relegated to science fiction, has gained traction among physicists as a possible explanation for dark matter's elusive nature. Imagine our universe as just one page in an infinite cosmic book, with dark matter acting as the faint ink bleeding through from the pages above and below. This isn't just poetic speculation. Some models suggest dark matter's gravitational oddities could stem from particles or forces leaking into our reality from adjacent dimensions, weaving unseen threads between parallel worlds. One compelling framework comes from string theory, which proposes extraspatial dimensions curled into shapes too tiny to perceive. In these hidden dimensions, entirely new particles might exist, interacting with our universe only through gravity. These bulk particles could manifest as dark matter, their influence felt but never directly seen. Think of it like a game of cosmic telephone. Vibrations from another dimension might reach us as ghostly gravitational tugs, warping galaxies in ways our standard physics can't explain. The Large Hadron Collider has even searched for evidence of these extra dimensions by looking for missing energy in particle collisions, energy that might have slipped into another realm. Even more radical is the idea that dark matter isn't just a passive bystander but an active bridge between universes. In brain cosmology, our universe floats like a membrane in a higher dimensional space, occasionally brushing against other brains. These collisions could transfer energy or matter, leaving behind dark matter as residue. It's a wild concept, but not without precedent. The Big Bang itself might have been triggered by such a collision, with dark matter as the lingering echo of that primordial event. Critics argue these ideas stretch plausibility, lacking direct evidence, yet the math holds surprising promise. Simulations show that multidimensional dark matter could naturally explain why galaxies rotate faster than visible matter allows, while avoiding the pitfalls of traditional particle models. And if dark matter does connect to other universes, it might leave subtle signatures like repeating patterns in the cosmic microwave background or anomalies in gravitational wave data. The beauty of these theories lies in their audacity. They don't just solve the dark matter puzzle, they redefine it, suggesting our universe is far stranger and more interconnected than we imagined. Whether they're proven right or wrong, they remind us that the cosmos still holds mysteries beyond our wildest dreams, And sometimes the boldest ideas are the ones that light the path forward. You don't need a PhD to help unravel the mysteries of dark matter, just an internet connection and a curious mind. Across the globe, citizen science projects are breaking down the walls of astrophysics, inviting everyday people to collaborate on cutting-edge research. Take Galaxy Zoo, one of the most successful initiatives of its kind. Launched in 2007, it tasked volunteers with classifying millions of galaxies from telescope images, a job too nuanced for algorithms but perfect for human intuition. The results were staggering. Within a year, over 50,000 participants had made classifications that led to the discovery of rare galaxy mergers and unexpected structures, clues that indirectly mapped dark matter's gravitational influence. This wasn't just busy work, it was genuine science driven by the collective power of curious individuals. What makes these projects so revolutionary is their ability to tackle problems that overwhelm even supercomputers. Dark matter research generates colossal datasets. Images from sky surveys like the Sloan Digital Sky Survey contain billions of celestial objects, each needing scrutiny. While AI can flag anomalies, human eyes excel at spotting the unusual. A warped galaxy hinting at dark matter's lensing effect, or a faint dwarf satellite orbiting a larger galaxy. Projects like Space Warps and Dark Energy Explorer harness this skill, asking volunteers to identify subtle distortions in space-time caused by dark matter's invisible mass. The collective aha moments of thousands of participants often reveal patterns machines miss, accelerating discoveries that would take professional astronomers years to uncover alone. But the impact goes beyond efficiency. Citizen science democratizes discovery, transforming passive observers into active contributors. A retired teacher in Portugal, a high school student in Indonesia, or a farmer in Kansas, all can share in the thrill of scientific breakthroughs. When volunteers in the Milky Way project spotted previously unknown gas clouds in our galaxy, their findings were published in peer-reviewed journals, credited right alongside career scientists. This inclusivity reshapes public perception of who does science, proving that curiosity, not credentials, fuels progress. The collaborative spirit extends to real-time problem-solving. On platforms like Zooniverse, volunteers and researchers chat in dedicated forums, debating oddball galaxies or troubleshooting classification challenges. These exchanges often spark new hypotheses, like the time Galaxy Zoo users noticed a strange green pea galaxy, a compact, glowing object that later helped astronomers study early star formation. Dark matter's puzzles are too vast for any one group to solve, but together, a global community can piece together clues faster than ever before. Yet the true brilliance of citizen science lies in its ripple effects. By engaging the public directly, these projects foster scientific literacy, inspiring future generations of astronomers. A child classifying galaxies today might be the one decoding dark matter's secrets tomorrow. And as telescopes like Vera Rubin and James Webb flood researchers with even more data, the need for human ingenuity will only grow. After all, dark matter isn't just a problem for scientists, it's a cosmic enigma we can all help solve, one click at a time. The realization that most of the universe is invisible forces us to confront a humbling truth. Our perception of reality is built on an illusion of completeness. We navigate the world through sight, touch, and electromagnetic signals, tools utterly blind to dark matter's pervasive presence. It's as if we've been studying an ocean by skimming its surface, unaware of the crushing depths beneath. This isn't just a scientific gap, it's a philosophical earthquake shaking the foundations of how we define real. If the majority of existence eludes our senses and instruments, can we trust our models of reality at all? Or are we like flatlanders, oblivious to dimensions beyond our comprehension? Consider how dark matter redefines the concept of matter itself. For centuries, science equated matter with tangible substance, atoms, molecules, things we could measure or manipulate. But dark matter shatters that assumption, proving that the universe's primary building block might be something entirely alien, indifferent to the forces that govern our everyday experience. This echoes the Copernican revolution, where Earth was dethroned as the center of the cosmos. Now, it's not our planet but our entire understanding of substance that's been demoted. The chair you're sitting on, the screen you're reading, these are cosmic exceptions, not the rule. The implications ripple into metaphysics. If reality is dominated by invisible, intangible mass, what does that say about other unseen forces, consciousness, dark energy, or even the nature of time? Philosophers have long debated whether reality is purely material or if there's an immaterial substrate. Dark matter doesn't answer that question, but it blurs the line between the two, presenting a third option. The material might exist in forms we can't yet perceive. It's a modern twist on Plato's cave, where shadows aren't just illusions but hints of a richer, hidden structure. Even our language struggles to accommodate this paradigm shift. Words like empty space or nothingness become meaningless when every cubic inch of the universe teems with dark matter's gravitational pull. Artists and writers have grappled with this dissonance, from the eerie darkness visible in Milton's Paradise Lost to the unsettling voids in Kubrick's 2001. These cultural reflections reveal a deeper unease. If the cosmos is mostly invisible, how do we reconcile our place within it? Are we the protagonists of this story, or merely bit players in a drama governed by forces we'll never fully grasp? The most profound lesson might be one of humility. Science often assumes that persistence and better tools will eventually reveal all secrets. But dark matter whispers a cautionary tale. Some truths resist revelation, not because of technological limits, but because they operate outside the framework of our perception. This doesn't mean surrender. It means expanding our definition of understanding. Perhaps reality isn't a puzzle to be solved, but a mystery to be explored, layer by elusive layer. And in that exploration, we don't just discover the universe, we rediscover ourselves, finite yet endlessly curious. Imagine plotting a course to Mars, carefully calculating the gravitational pulls of planets and moons, only to realize you've missed an invisible force shaping the entire journey. As space agencies prepare for crewed missions beyond Earth, dark matter's subtle but pervasive influence could become the next frontier in navigation. While its gravity is too diffuse to notice on planetary scales, over vast interstellar distances, even the faintest gravitational tugs add up. Future spacecraft traveling between stars might need to account for dark matter's distribution, like sailors charting ocean currents, using its unseen contours to slingshot through the galaxy more efficiently. This isn't just theoretical. The Voyager probes, now venturing beyond our solar system, have detected slight velocity anomalies, tiny deviations from their predicted paths. While most explanations point to outgassing or instrument quirks, some scientists speculate these could be whispers of dark matter's gravitational fingerprint. For missions like NASA's planned interstellar probe, targeting a launch in the 2030s, accounting for such effects could mean the difference between reaching Alpha Centauri or drifting endlessly off course. Advanced propulsion concepts like dark matter sails harnessing hypothetical weakly interacting particles remain speculative, but hint at how deeply this invisible substance might shape humanity's cosmic ambitions. The challenge lies in mapping the unseen. Just as early explorers needed accurate star charts, future astronauts will require 3D gravitational maps of dark matter's cosmic web. Projects like ESA's Euclid telescope are already plotting these hidden structures by observing how they distort light from distant galaxies. Over time, these maps could reveal gravitational highways, regions where dark matter's density subtly accelerates or decelerates spacecraft, allowing navigators to optimize trajectories. Picture a future where mission planners consult dark matter atlases alongside planetary alignments, treating the universe's hidden architecture as both obstacle and opportunity. Beyond navigation, dark matter could redefine spacecraft design. If certain particles interact even minimally with ordinary matter, as some theories suggest, prolonged exposure during decades-long voyages might cause cumulative effects. Shielding systems or detectors to monitor potential dark matter flux could become as standard as radiation protection. There's even the tantalizing possibility of using dark matter's gravity for propulsion. While still in the realm of speculation, concepts like gravity assist maneuvers around dark matter clumps could one day supplement traditional fuel, turning the universe's ghostly scaffolding into an interstellar fuel station. The stakes are higher than mere efficiency. Misjudging dark matter's role could have catastrophic consequences for multi-generational ships or fragile light sail probes. A slight miscalculation over light years might divert a colony ship into the void or strain a vessel's structure with unexpected tidal forces. This is why agencies like NASA now fund studies on dark matter astrodynamics, treating it not as an abstract puzzle but as a practical variable in humanity's expansion across the cosmos. What begins as a scientific curiosity today may tomorrow become mission-critical knowledge. Just as sailors once feared falling off the edge of a flat Earth, we're learning to navigate a universe where most of the map is written in invisible ink. The sooner we decipher it, the smoother our journey to the stars will be. The phantom galaxy paradox isn't just a scientific mystery, it's a humbling reminder that the universe operates on a scale far beyond our everyday perception. Every spiral arm of a galaxy, every cluster strewn across the cosmos, bears the fingerprints of an invisible architect, a force we've yet to fully comprehend. For all our telescopes and supercomputers, we're still piecing together a puzzle where most of the pieces refuse to glow. Yet this isn't a story of frustration, it's one of exhilarating possibility. The very fact that dark matter eludes us means we're standing on the brink of discovery, poised to rewrite the rules of physics as we know them. Consider how far we've come. A century ago, astronomers like Fritz Zwicky and Vera Rubin were dismissed as radicals for suggesting the universe held more than meets the eye. Today, their once controversial ideas are the foundation of modern cosmology. We've mapped dark matter's gravitational shadows across billions of light years, simulated its role in the birth of galaxies, and designed experiments so sensitive they could detect a whisper in a hurricane. Even the failures, the null results, the dead ends have sharpened our questions, guiding us toward smarter, bolder ways to probe the darkness. What makes this pursuit so extraordinary isn't just the science, it's the collaboration. From underground labs to space telescopes, from citizen scientists classifying galaxies to theorists dreaming up wild new particles, the hunt for dark matter has become one of humanity's greatest collective projects. It's a reminder that curiosity transcends borders, languages, and disciplines. Whether you're an astrophysicist crunching data or someone gazing up at the stars and wondering, you're part of this grand investigation. And let's not forget the bigger picture. Solving the dark matter enigma won't just fill a gap in our textbooks, it could unveil entirely new laws of nature, technologies we can't yet imagine, or even clues about the ultimate fate of the cosmos. Every time we peel back a layer of the universe's secrets, we're rewarded not just with answers, but with deeper, more beautiful questions. So as we close this chapter, remember, the night sky isn't just a static painting. It's a dynamic, evolving masterpiece, shaped by forces we're only beginning to understand. The phantom galaxy paradox invites us to keep looking, keep questioning, and stay awestruck by how much remains to be discovered. Who knows, the next breakthrough might come from a lab, a telescope, or even from you. Thanks for joining this journey into the unseen. If you enjoyed unraveling the mystery, don't forget to hit like, subscribe, and share your own cosmic ponderings in the comments below. The universe is full of secrets, and together we're just getting